Good morning, good evening, everybody. So we will start with the last day to our CaRT 25. And then the first talk of today is with Professor Gyula Károlyi. He's a research professor at the Alfred Renew Institute of Mathematics in Hungary. He's very active mathematician, editor, etc. So I met Gyula in Mexico many years ago, and we see for several times. In particular, I remember a trip to Oaxaca that Gyula made with his daughter. They visit Monte Albán, I think,
Yeah.
which is a very nice archaeological place here in Mexico. And they forget, Gyula forget because he's the father, yes. But really, he considered that as usual, they make a lot of trips in the forest and in the many excursions. They consider that it is not necessary use sunblock. So he knows my target side. When I saw his daughter, Borner, I expected. So after this day, I think that he doesn't forget Oaxaca and myself and me. So it's for me a place and an honor to introduce our invited speaker, Gyula Károlyi. Thank you very much.
Thanks, Rita, and thanks for the invitation. So I try to share my screen.
Mm-hmm.
Yeah. Mm-hmm. So how is it?
Okay, now it's okay.
Is it good?
Yes, this is good. Only if you can do this view full screen, maybe, or
it's getting worse and worse. Yeah.
or it can be in this way, depend of you.
I don't know.
You remember view in the top?
Oh, yeah. View.
Mm-hmm. Full screen.
Yeah.
Okay, now it's perfect. Thank you.
Good. Now, okay. So,
no, you
so
quit. You quit it. I don't know what do you do. Disappear.
Did I? Oh shit! Sorry. Okay, I will try again. No, my file is. I don't know what happened to my file.
Don't worry. This is a common factor to all the teachers. Everybody, we repeat and we forget how to do.
Okay. No. Okay, now I found it.
Okay, we can see.
View full screen. Oh, no.
Okay,
good.
Now it's perfect.
Yes, because this this sign that I am sharing the window appeared in the middle of my screen somehow, and I wanted to get rid of that, and that caused trouble. Anyway, so I'm finally here. I changed my title a little bit, although Turán theory is very closely related to Ramsey theory, and probably in this context it is a lot more hardcore mathematics, but I decided to not to touch that area to make this presentation more coherent. So I will only talk about Ramsey type results. So here is the overview. After a short introduction, I will talk about classical Ramsey type results for linear Diophantine equations. And in the second part, I will talk about nonlinear polynomial equations in an area where a lot of new interesting results were obtained during the last decade. And finally, I will say a few words about my modest contributions to this area. Okay, so what is the philosophy of the whole thing? If you have a very large structure, it tends to contain large substructures, configurations, which are unavoidable. Sometimes they are called homogeneous substructures. And here are a few examples. So most known is the realm of graphs, where these homogeneous substructures are the empty or complete graphs. Like here is an empty graph, here is a complete graph. Or you can talk about tournaments, complete directed graphs. And here what you cannot avoid are transitive subtournaments. You will always find a relatively large transitive subtournament, which looks like this. So if you order the vertices, every edge goes from left to right. Or if you consider sequences of real numbers, but you cannot avoid are monotone subsequences, either increasing or decreasing. You may find both, but at least one long monotone subsequence must occur. This is known as an Erdős-Szekeres lemma. If you don't know this, try to prove for yourself that among n squared plus 1 numbers arranged in a sequence, you either find a monotone increasing subsequence of n plus 1 numbers or a monotone decreasing subsequence of n plus 1 numbers. And an example from geometry, if you consider point sets in the plane, you cannot avoid large subsets in convex position, like here, they form the vertices of a convex polygon. This is known as the Erdős-Szekeres theorem. So for a second, let's have a look at graphs. So here I was talking about graphs in general, didn't say anything about coloring or so, but in a natural way, you can get to colorings. So for example, consider a graph on n vertices, like the blue graph, and consider its complement, the red graph. So together you see all the n choose 2, this time all the 10 edges. So these blue edges and the red edges form a partition of the edge set into two parts. And then what you can see is that one part must contain a large clique. So if this contains a large clique, we have a large clique. If this contains a large clique, we have a large empty subgraph, yes? Okay, with 5, this will not give you too much, but if you go to 6 vertices, this is the school example to demonstrate Ramsey's theorem. On 6 vertices, you can find a complete graph on 3 vertices, which is a triangle, either in the blue or the red color. So why? Just pick one vertex. There are 5 other vertices, so at least 3 of them must be connected to this vertex by an edge of the same color, blue here. And then you look at the neighbors. If you see a blue edge here, then you found a blue triangle. Otherwise, all the edges are red, and you found a red triangle. But on 5 vertices, you cannot always do that. This is something which can be immediately generalized. What if we partition the edge set into 3 or more parts instead of 2, like in this case? And we want to find a triangle or whose edges are of the same color. They are called monochromatic. So we partition the edges of the complete graph on M vertices into T colors, into T color classes. And this goes back to Schur, more than 100 years ago, who proved something like this. If n is large enough, then there is a class, one of these T classes, which contains a triangle. So I assign colors to the classes. I find a monochromatic triangle. And the proof is the same as this proof was. This time, pick a vertex. There are 3 different type of edges going out, but if I have enough points, then at least 6 of the edges must have the same color, say red, yeah? Now there are these 6 neighbors. If you see a red edge here, then you found a red triangle. Otherwise, all the edges in this induced subgraph must be colored either blue or green. Yes, so we are back to the previous case. And we are done for t equals 3. And you can generalize this argument, which gives you a nice recursion, which you can solve. And actually, if you are careful enough, you can improve this a little bit. Here I just put this one so that everyone sees that this happens, because for t equals 2, the bound was 6. And every time you multiply the number of vertices roughly by t, but a little bit less, so you can win something here. Actually, it's exactly computed in Schur's work, although Schur didn't state this theorem directly, but it appeared in an application which I want to show you. And this leads us to the realm of Diophantine equations. So what Schur really studied was this equation, x plus y equals z. And what he proved about this equation is that if n is large enough, how large? At least this large as this Ramsey number, which we discussed on the previous slide, small as positive integer n, such that if in every t coloring of the edges of the complete graph on n vertices, there is a monochromatic triangle. So he proved that directly that if n is at least this Ramsey number, then there is a class in this partition which contains a solution of this equation. So contains three numbers, x, y, and z, such that x plus y equals z. Yeah. So here, of course, these numbers cannot be the same because they are all positive. And here is the proof. You color the edges of the complete graph and vertices using T colors. These T colors will correspond to the parts of this partition. Such a way, if A is less than B, then we color the edge, AB, by the color I if their difference lies in the i's part. Yeah, it must be lie somewhere. Actually, it would have been enough to consider a complete graph on n-1 vertices, but doesn't matter too much. So what happens if you find a monochromatic triangle in the color I? That means that B minus A, C minus B, and C minus A have the same color. And if you add up the first two, you get the three. So this proves Schur's theorem. This was the first Ramsey type result, which was ever discovered, although not in this 2 days terminology about colorings and graphs, etc. So why is this theorem interesting? How did Schur? You know the name of Schur. He is known from many different areas of mathematics. There are at least 10 theorems or lemmas named after him. He was interested in Fermat's last equation, the last theorem. So you have this Fermat equation, x to the t plus y to the t equals c to the t at least 3, because for 1 it's trivial, for 2 we know the Pythagorean triples. There is a complete characterization. There are infinitely many such triples. But if t is at least 3, this equation, this Diophantine equation, has only trivial solutions, namely when one of the variables equals 0. Yeah, this is Fermat's last theorem, which was a conjecture, very famous conjecture for a long time, until Andrew Weiss finally proved it. And Schur's idea was the following. Suppose that there are infinitely many prime numbers p, such that this equation has only trivial solutions modulo p. Yeah, this means one of the numbers is a multiple of p, so it's congruent to 0 modulo p. What happens then? For infinitely many prime numbers, because there are only 3 variables, one variable in a solution must be divisible by p for infinitely many p's, which only can happen if its value is 0, right? So this would imply Fermat's last theorem immediately. But alas, Schur found out, using this theorem on the equation x plus y equals z, that this is not so. If the prime is bigger than this Ramsey number, then the equation has non-trivial solutions modulo p. So you cannot prove Fermat's last theorem, just based on such modular obstructions. Okay, so this is where it began, and roughly 10 years later, van der Waerden obtained another remarkable results about the equation x plus y equals 2 times z. What does this mean? It means that z is the average of x and y, so x, z, and y in this order form a three-term arithmetic progression. Here is an observation. If you have 9 consecutive integers from 1 to 9, then you will find 3 numbers of the so you divide them into 2 parts, say color them with 2 colors. Then there will be a monochromatic triple like this, which is a solution of the equation. So you find a monochromatic non-constant arithmetic progression, no matter how you partition this set into 2 parts. And here is a counterexample for n equals 8. So this 9 is sharp in the theorem. Here you don't see either a blue or a red arithmetic progression, right? And van der Waerden proved that this is true not only if you use 2 colors, but you may use any number of colors, say t colors, and you can find arbitrarily long arithmetic progressions, assuming that you have enough numbers. N is large enough. You go from 1 to n. If n is large enough, you color this set with t colors, you will find an L-term arithmetic progression, which is non-constant. Yeah. And the smallest such n when this happens is denoted by WTL, W for van der Waerden. Yeah, so in this terminology, this simple example shows that W23, 2 parts, 3-term progressions, is 9. Well, 3-term progressions belong to a single equation. Longer progressions can be characterized or described by a system of linear equations like this. Yeah, this means that the first 3 form an arithmetic progression which overlaps with the next one. So the common difference here should be the same, and so on. In the end, a solution corresponds to an L-term arithmetic progression. So just you may wonder, how can you bound these van der Waerden numbers? In Rado's in Schur's example, there was this nice bound, yes? Well, van der Waerden's proof is on double induction, using double induction, and is very intricate, and it yields to the existence of these numbers, but they are enormous. I mean, you cannot imagine how large them. For example, what comes out from van der Waerden's argument for 3 colors and 3-term arithmetic progressions is already, I mean, unimaginably large. So let's stay with two colors only. Probably this van der Waerden function in that case is not that unimaginable. And Graham, over one of the greatest money prizes, which used to be Erdős's habit, for proving that this number is bounded by 2 to the k squared, say. What can we know from below? from below, we know that this number is exponentially large, which was proven by Berlekamp in 1926 by a beautiful algebraic construction. The P comes from the algebraic construction. It's a prime. And if you take into consideration the gaps between primes, you get the general bound of this form. 2 to the k divided by some smaller quantity. And I just recall this result of Zoltán Szabó, who improved this bound, proving this exponential bound 2 to the k divided by some function which tends to infinity very slowly. So epsilon here can be arbitrarily small, like 0.01. So, and why I mentioned this theorem of Szabó, he used this applying the probabilistic method, namely Lovász's local lemma, and he obtained this result when he was still a student at Eötvös University. And to the best of my knowledge, even today, this is the best known lower bound. So for more than 2 colors, this is the best general upper bound, which is due to Timothy Gowers. And this bound of his is closely related to the work for which he received the Fields Medal. You see, this is still something nervous. But before, nothing which you can imagine and can write down on a sheet of paper was known. So that's the 2 main classical results, and I want to mention something which is a common generalization. And this appeared in Richard Rado's dissertation, who generalized these theorems for finite systems of linear Diophantine equations. So consider such a system. It can consist only of one single equation, but you may include more than one equation, but only a finite number of them, like we did in the van der Waerden's case here. He says that such a system is k-regular if there is maybe very large natural number n, such that if you color the set of these numbers by k colors, then the system of equation will contain a monochromatic solution. It will contain a monochromatic solution to the system of these linear equations. So is the concept clear? We had these two equations, x plus y equals z, x plus y equals 2z. They satisfy this condition for every k. An equivalent formulation is that every k coloring of all natural numbers will contain such a monochromatic solution. One direction is obvious, the other is kind of a compactness argument. And we call the system regular if it is k-regular for every k, like in Schur's or van der Waerden's example. And Rado gave a complete characterization of such regular systems of linear equations which implies both Schur's theorem and van der Waerden's theorem. But here, you may wonder whether Rado was cheating, because here this equation, for example, has a constant solution, x, y, z equals to 1. Also, x, y, z equals to 3 is another solution. And such a solution is monochromatic in every coloring because they are the same thing. So if x is red, then y and z equaling x is also red. So for this trivial reason, this equation is regular. So how comes that Rado's characterization works for van der Waerden's theorem? I mean, it seems it only gives that, well, this in every coloring has a monochromatic solution, but this obviously happens. You don't need this deep theorem of van der Waerden. Maybe he really didn't prove that, but there is no cheating here. Here is Rado's trick. You had this system of equations which defined the L-term arithmetic progressions, and you just simply add another equation such a way that the whole system still can be seen to satisfy Rado's conditions. Then you really get a non-trivial, a non-constant arithmetic progression, a monochromatic non-constant arithmetic progression by Rado's theorem. So it really generalizes van der Waerden's theorem, and actually it yields a stronger version, because if you look here, this xl plus y, the new variable we introduced, equals xl minus 1 minus xl, which is the xl minus xl minus 1, which is the common difference of the arithmetic progression. So not only all the elements of the arithmetic progression will have the same color, but also the common difference of the progression will have this very same color. Let's see what Rado's condition says if you have just one linear equation. At least two variables, of course, otherwise it's trivial. And let's say this equation is homogeneous. This is easier to understand. So these equations are non-zero. I have indeed k variables appearing here. And Rado's condition is that this equation is regular, meaning that in every finite coloring of the set of positive integers, there is a monochromatic solution, if and only if some, maybe all, but at least some of them, these coefficients a sub I add up to 0. You find a non-empty subset of the indices such that the sum of a sub i's in this set of indices equals 0. So if you look here, this equation is not regular by this condition, because you can rearrange it like this, and among these coefficients 1, 1, and minus 3, there is no partial subsum which equals 0. On the other hand, this other equation is regular. Actually, here Rado's condition can be applied two ways. If you see 2 plus 1 minus 3 equals 0, so these three coefficients add up to 0, but also these two coefficients add up to 0. So this is regular by two different reasons. Okay? So what happens for non- or inhomogeneous equations? Without going to technical details here, let me just show you a shifting trick, which shows that x plus y equals z plus 1 is regular. Moreover, it it has non-constant monochromatic solutions in any finite coloring of the natural numbers. And the trick is the following. Here you have your coloring of the integers, and you construct a new coloring by shifting this coloring to the left by 1. This is a new coloring. And in this new coloring, you look at Schur's equations, for we know it is regular, and it cannot have constant solutions. So if you find a solution here, you just add 1 to each A, B, and C. So you shift this solution back here by 1, and then A plus 1, B plus 1, C plus 1 will be a solution to the original equation. So this is a nice shifting trick. And basically, using this trick and an enlargement trick, you can get to conditions for inhomogeneous equations. Okay, so you see we had this problem of constant solutions, which didn't occur in Schur's case, but occurred in van der Waerden's case. And in the sequel, in the second part, we have to say something about them. So I will talk about non-trivial regularity, by which we mean what it should be. So if you have a constant solution to some polynomial Diophantine equation, then the equation is regular, because this will be always a monochromatic solution. And we want to exclude such trivialities, and we say that the equation is non-trivially partition regular if in every finite coloring of the natural numbers there is a non-constant monochromatic solution. And we say that its partition irregular in the otherwise. Don't care about this. I will not use this notation. I will use PR for regularity. Yes, one thing I forgot to write here, but it can be seen easily that an equation is non-trivially partition regular if and only if in every finite coloring of the natural numbers there is not only one but infinitely many non-constant monochromatic solutions. Why is that? The reason is that if you see only finitely many such solutions, they can be destroyed introducing new colors, coloring numbers appearing in these finitely many solutions. We use some new colors, and then eventually we find a coloring which contains no non-constant monochromatic solution at all. So containing at least one in this case means every finite coloring contains infinitely many monochromatic solutions. And here are some examples. This was Schur examples. It's partition regular, and there are no constant solutions at all. Van der Waerden's equation was non-trivially partition regular. It had constant solutions. Now this one, I just modified this a little bit, is not regular at all, not even too regular, because of parity reasons. If you see a solution, X and Y must have different parity, right? So if you color the even numbers red, the odd numbers blue, then in every solution you see a blue and a red number at the same time. And just to move slightly to the realm of nonlinear equations, consider this one. X plus y equals z squared. Now it is known to be partition regular. It is not regular. It is regular for an obvious reason. There is this trivial solution. 2 plus 2 equals 2 squared. So it is regular, but not non-trivially regular, which means partition irregular. We will see why. So here this distinction was important. This really doesn't happen in the realm of linear equations or systems of linear equations, because it was shown by Hinman and Leader that a system of linear equations in at least 3 variables, if it is regular, then it is also non-trivially regular, like van der Waerden's. It is regular for an obvious reason, non-constant arithmetic progressions, but as van der Waerden's theorem states, it's non-trivially partition regular, and this is a phenomenon which holds for linear equations or systems of linear equations in general. But as you see in this example, it is not true anymore for higher or degree Diophantine equations. So let's have a closer look at this equation. This appeared in a work of Chikwari, Yarmati, and Sarkozy, who noticed that this equation was partition irregular because they exhibited a 16 coloring defined using some congruence systems. A 16 coloring in which you don't find a monochromatic solution unless it's then constant solution x, y, z equals 2. And later, Green and Lindquist observed that you don't need 16 colors and intricate congruence systems to find such coloring, because some sort of greedy 3 coloring will do the same. Actually, this is a simple argument. This one was a complicated argument. So the simpler the statement, the simpler the argument became. On the other hand, if you color the numbers only using 2 colors, then you will find infinitely many monochromatic solutions. This proof is really complex. It's like 25 pages and using a lot of different ideas. But Peter Poch, roughly at the same time, found a very simple elementary proof of the same result. And where my work started on this problem, this kind of problems, was related to this equation, where I found an explicit 3 coloring. So here, using the congruence systems, this coloring is explicit. This one is not. This is given by an algorithm, although it turns out that this algorithm can be turned into an explicit coloring, which is very similar to the one I found. So I found this roughly at the same time as these things happened, but then I learned it was during a workshop for graduate students on additive combinatorics, and there was a problem sheet, and there was this problem on the problem sheet, showed that this was not partition regular, and I looked at the problem sheet, and I found this coloring, which I will describe you later. But I abandoned this thing because then I learned that this was known basically by Green and Lindqvist, the same very similar coloring was found. So it could be the end of my story, but it actually starts here. Now here I collected some more examples, which I probably, well, I just, let me mention one. In 2018, so roughly at the very same time, Dinasso and Riggio wrote a paper in Combinatorica about Fermat-like equations, which were not which were partition irregular. What did I? Oh, here, this is a mistake. They are partition irregular. Sorry, forget this. And they used transfinite methods to show these kind of results, and they had many different results, but in a most simple formulation, it works for equations like this. Notice that the true Fermat's equation is not here. This should be not in M and N. So this exponent in their result is different from these exponents, which may be the same, but K is different. Sorry, K is not in the set M and N, and this equation is partition irregular. But these results were all obtained using transfinite methods like ultrafilters and non-standard analysis, which say nothing about how many colors do you need to prove that the equation is not non-trivially partition regular, so it's partition irregular. You cannot get any idea. And here is an interesting question of Erdős and Graham from 1975, which says that equation corresponding to Pythagorean triples, whether it is regular or not, it is still widely open, and it is only known since 10 years that it is indeed two regular in any partition into two classes of the natural numbers. You will find a monochromatic Pythagorean triple. But this is a computer-assisted proof, which is the longest computer-assisted proof ever written. It's the proof is contained in a file of 200 terabytes. Incredible. So how this explicit coloring looks like? This is a family of colorings I constructed. Let T be an integer which is at least 3, and alpha be a real number which is bigger than 1. And the coloring is defined as follows. for every integer, we choose a color, which is a number between 0 and t minus 1. Actually, it's a residue class modulo t. And it is defined as follows. If n is at least 2, then you can find a unique non-negative integer k, so that n lies between 2 powers of 2, and the exponents are alpha to the k and alpha to the k plus 1, respectively. And we define the color of n according to the residue of this exponent modulo t. So here is a figure showing this. You start with the color 0, then you have color 1, then more numbers of color 2, then many more numbers of color 0 again, then t equals 3, then many more numbers of color 1, and so on. So here you have longer and longer intervals in which numbers have the same color, and the length of these intervals grows double exponentially. And it is in some ways it's cyclic, so it's like 0, 1, 2, 0, 1, 2, 0, 1, 2, and so on. So this is the coloring. How did I find this coloring? Let's see the idea. So I wanted to prove that this equation was partitionally regular. So I wanted to show this using as few colors as possible, and to have some control on this coloring, I divided this. I imagine that this set of positive integers is divided into intervals, which are colored cyclically, say with 3 colors, or if 3 is not enough, then maybe with 4 colors. But it has a cyclic nature, this coloring. Okay, so I color consecutive intervals in a cyclic manner. This was the idea. And if I look at this equation, I notice that at least one of x and y in a solution must be, of course, they are both less than z squared, but at least one of them must be at least half z squared, which gives some control on this larger number x in the solution. Why we cannot control it? This may be very, very small. We cannot control with these intervals, but x we can control. We can control the color of x if the following things happens. I chose the lengths of intervals so that if z lies in a certain interval, then both z squared over 2 and z squared, which lies to the right of z, lies in a different interval, but not too far away, not too far apart. Maybe it lies in the next 2 intervals, and since x is in between them, it has a different color than that of z. So the solution cannot be monochromatic if I can achieve this. And this gives conditions, algebraic conditions on the endpoints of the intervals, which you can work out. And this is how such a strange coloring was found. But now this coloring can be used to obtain a lot more results. Here is the proof in a pure form. You can use the same argument for other equations, like I like this one very much. This is a Fermat-like equation, and partition regularity cannot be proven by these results of which appeared in Combinatorica. But with this, you can prove partition irregularity using only 3 colors. And this is a Fermat-like equation which has a lot of solutions. They tend to have only solutions in a finite number of infinite sequences, but here are more such infinite sequences which can be parameterized. So it has many solutions, and so on. This can be a nice exercise to prove the partition irregularity using this coloring. I show how to choose the parameters, 3 colors, and you can choose alpha to be 2, except like square root 2 in the original problem. And here I have some more general theorems, but probably I have to finish my talk here. So thanks for being with me.
So thank you very much, Gyula. I don't know if somebody has question, comment. Yes, William.
I have a question. I was wondering, when you talk about the bound for van der Waerden
Yes.
result, you told us that W23 is 9. But I
This
don't
one?
know. W23 is equal to 9.
W23 is equal to 9, yes.
But do you know, or is it known a few more small examples? Well, small cases
Can you
from.
talk a little bit louder?
Yeah, is it known any another example, another T and L?
Yes. So there some values are known. For example, this W33 is something about 30.
Oh, so the bound
But
is.
from the intricate inductive argument, you can only find this bound, but you can it can be proven that it's something like 35 maybe, or 28, something like that. So some small numbers are known.
Okay, so
Yes.
the bound is like really far from the result.
So van der Waerden's bound, I mean, what you can get from the proof is very large. Yes.
Thank you.
But for general T and K, there were some bounds which use the Ackermann function before Gowers got this bound, which was a huge achievement. Actually,
thank you.
to get this bound, he used harmonic analysis, and he introduced a set of new norms, which is now known as Gowers norms, and very powerful tool. If you fix K to be 3, so you are looking for 3 progressions, and you may have more colors. Now, a lot of improvements appeared lately in a series of works of like Burgens, Sanders, and others. It started with Graham and Shoimoshi. So it's for K equals 3, there is a reasonable bound.
Super. Thank you.
Any more question? Comment? No, okay. I just like to say thank you very much, Gyula, for this very beautiful, nice talk. I it's always nice to see that the mathematics are not a solitary person, yes? So in your talk, we have algebra, we have number theory, we have analysis,
Yeah,
rhetoric. So this is very nice. Thank you. And
yeah, part of my aim was to show that also some naive approach can be used instead of these non-standard analyses and things like that to get results too.
yeah, I think this is very important to our students to look that it's not maybe the best just concentrating one area, because sometimes they say, oh, I am not interested in talks in different things because they consider that he can continue only one line, but I think that this is very good to see that it doesn't happen really. And your proof is really very nice idea to take this periodic. This is great. So I am very happy that you shared with us this idea. Thank you very much.
Thank you, Rita. And I have to say goodbye to you because my sister is waiting for me and I have to leave now. But I wish you a nice conference in the remaining hour. Okay.
So thank you very much, and thank you to be with us, not only like invited speaker, you were with us during all the conferences.
Yeah,
Thank you very
yeah.
much.
It was
See
a
you.
pleasure.
And goodbye.
See you. Bye-bye.
Okay. Thank you. So maybe we take 2 minutes just to have time to continue with the next talk. Okay, thank you.